and because we're talking about language and being annoying with language, a chlorine was added. Yeah, is a good way to go. Would be substituted. Okay. We want to avoid the added term because if we're saying added, that sounds an awful lot like addition, and we're not talking about any pi bonds. Right? Right? So this does look like substitution. Right? Is it regular substitution or is it radical substitution? It's a much harder question. To figure out radical, we said we had to look for alkane, rohr, or light. Rohr and light are a reagent. And we're SOL on that because I haven't specified any reagents. Right? So to differentiate between radical substitution and substitution, the only other piece we've got to go by is
Substitution.
Is it an alkane?
No. Aldehyde? Is that an alkane?
Oh, so this becomes the challenge. Because we now have to look at this functional group and what's reacting and decide what makes it an alkane, what makes it an aldehyde. Okay, so here you were a little questionable on it, so let's change the structure a little bit. Is that red hydrogen any different than the red hydrogen in the original reaction?
Yeah, because it's so far away from
Okay,
the...
well, this whole... You probably said too much already anyway. So this side of the classroom, are those red hydrogens different? Yeah? Why?
It's connected to a carbon, which is reduction of carbon.
Right? It's connected to a carbon that's connected to a carbon, but isn't this one connected to a carbon that's connected to a carbon?
Yes, yes. But it's connected to an oxygen.
Okay. But then it's connected to an oxygen. Okay, so you're saying that somehow affects the chemistry. Okay? So if we were going to go through and reference this red hydrogen, what functional group might we call that? That's probably fine calling that an alkane. Should we call that one an alkane? Okay. And the question that you might be thinking is, well, if I can't call it an alkane, what should I call it? Which is a really valid question, okay? And we could use other examples for that, okay, which we have used in the past, okay? How would I label that hydrogen's chemical functional group?
Alcohol?
You'd label that as an alcohol. That's fantastic, except if I did this,
That's carboxylic acid.
it's a carboxylic acid. So now we have different names associated with it, and those names came about based off of the proximity of the functional groups. Those functional groups' proximity could talk to each other, okay? And in the case of the carboxylic acid, its chemistry changes, and that hydrogen becomes acidic because why? Ooh, we have this resonance possibility. Okay? So if we go back up to our questionable red hydrogen, and we're like, well, I don't want to call that an alkane, what do I call it? Do you have to call it anything? Okay? Said potentially another way, one of our reagents in the first unit was the Lucas reagent. Are you responsible for knowing what the Lucas reagent is? Let's try it this way. How many people know what the Lucas reagent is? Show of hands. What's the Lucas reagent? So we're looking at half the class. So what do you guys think? Should the other half of the class know what the Lucas reagent is? Okay. So we got some people saying yes. You're saying no. You're saying no because we had a conversation about it. Okay. But why no? Why do you need to know the name? Okay? The only reason we have names is to clarify communication. If I've got a structure and I can show that that hydrogen is different reactivity than an alkane, do I need to name it? I have another way of showing that it's different chemistry. So I could go through and use a name, and depending on the perspective of the person going through and doing it, they may say, we need to define that name. How important have names been in this class? Right? How many times have I said Morkovnikov without throwing up? Okay? Names aren't critical to an understanding of what's happening. What's critical is, do we understand the chemistry associated with it? So if we're going to look at the location of that hydrogen, is its chemistry distinctly different from an alkane? And if so, how? If it leaves or if it gets taken, those are two very different things. So if it leaves, what are we saying happens? If hydrogen leaves, hydrogen took the electrons. That's what leaves means. That's H minus. What would be the carbon? Positive. Is that a good thing to do? No? Why not?
Hydrogen is so small. I mean, another negative or another electron on it is just going to make it so unstable.
Cool. Way to take the easy answer. Hydride, shitty unstable. Okay? Hydride is the smallest, effectively least electronegative element. There's no resonance. There's no induction. There is nothing to stabilize that negative charge. That's bad. What about the hard answer? What about that carbocation?
You get a positive oxygen, try to stabilize the carbon.
If I tried to stabilize the carbon by doing what?
Resonance.
Resonance. Okay? Which is a lovely idea. Oh, I can do resonance. Can you? Take a look at the electrons that you're talking about moving. Where are those green electrons going to move? They're going to move towards the most electronegative, to the oxygen. They are never going to rotate down to stabilize that positive. So is there resonance? No. Okay, so what does that suggest about hydrogen leaving now that we've killed that one? That was a bad idea, right? My pen's not working, but maybe it'll start working in a little bit. There we go. Bad idea. What was the other option? It gets taken. If it gets taken, what happens? What would take the hydrogen? Okay. The thing that would come in and take that hydrogen would be something like a base that supplies electrons. Those electrons could come in, which then means the electrons in that bond go where? Towards the carbon. So we could look at that hydrogen being positive, or we could look at it being neutral, connected to the base. However you want to evaluate that, I'm fine with that. Is a negative carbon a good thing? No. Well, if a negative carbon is a good thing, or not a good thing, that would suggest that this has very similar chemistry to an alkane. We could just call it an alkane. Am I actually looking at a negative carbon? And this is where we get a couple different answers. I heard someone say no. I heard someone say a half negative. Okay, that carbon is absolutely 100. That's a negative. I don't understand what you're talking about. Okay, what you're saying is, what can I do with that negative?
Resonance.
I can do resonance, and when I draw out that resonance structure, that carbon is no longer negative, which for the person saying it was half negative We're evaluating both resonance structures as contributors to the overall diagram or the understanding of the reactivity of that hydrogen, and therefore it is only a half negative. A half negative is actually pretty stable because it's not formally negative. Okay? Another person said, nope, it's not a negative carbon because they're only looking at this resonance structure. Okay? But is this new resonance structure done?
You're going to charge on
The oxygen is still negatively charged, which I would then hazard a statement. Which of these two resonance structures should you be using to evaluate the success of whether this reaction happens? Of course it is the correct one. Which one's the correct one? The one with the negative oxygen. Okay? Why is the negative oxygen one the best? Oxygen is the most electronegative, which means if I'm going to evaluate whether this chemical reaction that I'm going to do works, I can look at my best resonance structure and I can compare that back to the stability of my reactants. We said we added a base. What's a good base to add? OH negative. And if I'm now comparing back and forth on this, OH minus versus O minus, which one's more stable? O minus versus O minus, which one's more stable?
the one with resonance.
Okay, nice dodge. We start looking at charge. They're both the same charge. We can move to atom size. They're both oxygen. They have the same size. We can move to electronegativity. They both have the same electronegativity because it's oxygen and oxygen. We can then evaluate resonance and say that this bottom structure has that resonance boost, which means that chemical reaction is going to progress this way. Okay? So is that hydrogen acting differently than an alkane? Yeah. Okay? And I could go through and try and come up with some kind of name for this hydrogen. And I might actually be right. I honestly don't know because I haven't actually looked at a name. We might call that hydrogen. What functional group do we have here? Technically, we've got a hybrid thing with the aldehyde going on with it. Okay, but if we just look at the right-hand side of it, that's an enolate, we're looking at effectively steps of the enol mechanism, our keto-enol tautomerization. We might refer to that hydrogen as enolic because it's able to be removed through a keto-enol tautomerization. Okay? This should give us two pieces of information. Number one, we're not doing radicals, we're doing substitution. Number two, did I find out a reagent I needed?
Base.
I now know I need to have a base to run this chemical reaction. Awesome. Okay. Does that base get me to my final answer?
No.
No. Okay. So now I would have to consider how can I get from this acid-base reaction to a final answer. And I know I have to remove the hydrogen because that was one of the identified things that I said I had to get rid of. So now I can say, well, of these two resonance structures, which one should I use to continue my thought process for a chemical reaction? Why the one on the left? Didn't we say the one on the right was the best?
For understanding why you should use a certain base, I guess, for understanding
Yeah.
reagents.
So our resonance structures, we will kind of oscillate back and forth on depending on what we're trying to do. If we're trying to predict the success of a single reaction going forward, we look at the best resonance structure. If we're trying to decide how that structure chemically reacts, we're not going to look at the best, we're going to look at the useful one. Why would we not look at the best? Well, why was it best? It's the most stable. Don't use the most stable thing to chemically react. It's stable. It's not going to. Okay? Which then means when I look at my system, I'm looking at how I can convert. Maybe I can use an arrow pointer for people at home. How I can convert, whoops, that was not the right place to draw. Point. Let's try up here. How I can convert that carbon into, where did it go? That carbon of my product. Well, what changed?
I
The halide was added, which means as a reagent, what do I think I need to show in there? What has to appear? Do better than a halide. Come back to that.
CO2?
I need Cl. Chlorine has to be there. So chlorine has to be there. Do I know more than just chlorine? Because is this chloride with a negative? No. Because I followed this process out, I know my carbon's coming in as the negative, which means the chlorine must be positive. And that should set up all sorts of alarms, because how can I possibly get a positive chlorine? I would need to connect it to an electronegative element. What electronegative element could I connect it to? I could connect it to chlorine. So now, running through this process, I know that I need sodium hydroxide and chlorine to run this chemical reaction. I now know the reagents. I didn't have to memorize anything. By looking at what the changes are and then highlighting each of those steps to understand how can I navigate that system. And this doesn't always work, because there will be cases where you're like, I have no idea how these individual steps can possibly happen. Okay? Because even navigating this, you had to think through each of those things, which requires time. Ideally, you would have had some of it memorized. And if you had some of it memorized, you could jump to the answer faster. That's okay. But it's going to be impossible to memorize everything. So we need to work through how we can identify those changes to help us kind of compartmentalize and navigate through those individual answers. Okay? And I'm happy if people take pictures. That's perfectly all right. And this becomes the next thing that I'll leverage and be kind of irritating about. What you see up here is what?
Just one example.
One example. It's also the answer. Where should your notes be? The mechanism's there. So is copying the mechanism?
Putting words,
What words?
explaining.
The words that came out of my mouth. Every question I asked that you answered to navigate this, that's your notes. And I talk a lot, right? No one wants to write all those notes. But that's your thought process. That's what you're supposed to be navigating through every time you tackle a question. Kind of, sort of?
So would it be like an acid-based then a substitution?
Say again?
Would it be an acid-based then a substitution?
Okay, so there's a cool question. What kind of chemical reaction happened? Okay. Beginning to end, that's substitution. What were the individual mechanistic steps that happened along the way? You're now asking a different question. That first mechanistic step was
Acid base.
purely acid base. Okay? What was that next mechanistic step? Okay? And this is where things become dangerous. Is substitution a mechanism? No. Substitution is not a mechanism, it's an overall reaction. What are the mechanisms that you've seen within substitution?
It's 1 and SN2.
You might say SN1 and SN2, which is not a bad answer, except SN1 is actually not technically mechanistic steps, because what is SN1?
How would you describe mechanism? Like this?
Okay? And yeah, the word is dangerous because we don't use the word in the same context, in the same meaning all the way through. Because there's mechanisms that say how we got from beginning to end is the whole mechanism. And then the thing that I would actually push to that you want to get at right in here is what are the elementary mechanistic steps? What are the individual things that you had to do to navigate this? So in this first case, we had to do an acid base. In this second case, It's not a substitution. It's not an SN2, because in SN2 I need a leaving group, but there's no leaving group. Actually, you could make the argument your chlorine is a leaving group. You could make the argument that that's actually a substitution in SN2. I got that backwards. Sorry. Okay. Where our electrophile, our substrate, is actually the chlorine. What's our nucleophile?
Negative carbon.
The giant carbon, negative carbon structure. Okay? And that becomes, even for me, just there, I screwed it up, a kind of natural response is that we tend to say the carbon structure is our primary thing that's being acted on. In this case, the carbon isn't the thing being acted on, it's the one doing the acting. So it changes how we would label things. The substrate is our chlorine, our nucleophile is this, we're running an SN2 reaction here. Okay? SN1 is a mechanism beginning to end that has different elementary mechanistic steps. SN2, since it's all done at once, is in and of itself an elementary mechanistic step. So an SN2 is an overall mechanism and an elementary step. Kind of, sort of? So cool, are we happy with that? Do you all have questions about it? Cool, I have another question then. I'm going to clean it all up. Can I erase a bunch of stuff? Yeah. Okay, so we're going to do, remember what's up here, because we're going to make some adjustments within this. We'll clean this all up. And hopefully I don't screw it up and make adjustments. Change our structures. What adjustments did I make? What?
Sodium.
Did I not write sodium hydroxide the last time?
You just wrote over it. You did.
No,
Yeah,
at
you
the top you want
You were doing the reagents in the wrong order?
Ah, okay. So if we're looking at this, when I initially wrote it, I wrote, in theory, I thought I had sodium on it. Sodium hydroxide, then underneath it I wrote chlorine. Why did I write it in that order?
Because you wanted the acid base to go first.
I was writing it in a way that helped me understand how mechanistically I used that to navigate that process. That's why I put it there. If we look at how it's written now, is it written in that order? No. Why not? Dangerous question because I don't know an official answer. Why do you think it is now changed? No, like pessimistic thoughts about why you think it's changed? I mean, that's not interesting. That's not bad. Cl2 is more dangerous. Like, you don't want to deal with chlorine gas. Okay. I would say the initial pessimistic answer from students would be because it's more difficult to understand what's going on now. Because I would have looked at the chlorine first and tried to make the chlorine react right away. Right? Screw organic chemists just trying to mess with students. I don't think that's the case. I really don't. Right? What I would bet this is going to come down to is kind of the importance of those individual reagents. The sodium hydroxide as a reagent is just a base to effectively catalyze and facilitate this reaction, so it has a lesser importance overall because even without the base, this chemical reaction will happen. Why? That red hydrogen is acidic enough that the ketone could actually deprotonate it. Not a lot, but it would do it. So the addition of the sodium hydroxide is really just to speed the chemical reaction along. Okay, so it makes the reaction much easier, much faster, and all of that. That's why it's playing it's a secondary role and written underneath the arrow. Okay. So now, next question. What was the first step of our reaction? So deleted all that. Acid base. Cool. Okay, what was our base? NaOH. As a base, what acid does it react with?
Or what acid is that?
This is a really weird question, but it's a really important one.
So what?
If I throw a base into solution, what does the base react with? It reacts with the H+. Well, what H+? Ooh, all of them? That's actually a no. It doesn't react with all of them. Ah, there's an important distinction. It reacts with the most acidic hydrogen. Right? So when we're now evaluating or looking at this chemical reaction, we have to be aware that we're in huge amounts of each of those chemicals. We've got thousands of all of these around. So this chemical reaction is going to happen, and it's going to convert one of my starting materials into my product. So now when I think about the next step of this chemical reaction, I'm not mixing sodium hydroxide with my starting material, or really not mixing it with only my starting material. I'm also mixing it with my product. So when I now consider that I'm adding a base, that base is going to react with the most acidic hydrogen. Where is the most acidic hydrogen?
On the chlorine structure.
Why is the chlorine structure, we'll call it the green hydrogen, more acidic than the red hydrogen?
Because of inductive effects.
It has the same resonance opportunities as the red one, but now that green hydrogen has a chlorine nearby, and there's an inductive withdrawal of electrons. That induction is going to make that green hydrogen even more acidic than the starting material. And because that's the case, what does our base do? It's going to react with that green hydrogen, and it's going to make a whole bunch more products. Or really, product. Okay? And it continues through that mechanism that we drew out. I think I oversimplified that mechanism as two-step. Could be wrong on it. Okay? We would have our old chlorine on there from the first substitution, and then we would get another chlorine for our next substitution. And now we could say, ta-da, finally, this is my answer. Why is this a problem? Okay? Again, I look at that product. I guess we're going to make it a purple hydrogen now. We're starting to run out of colors. That purple hydrogen is even more acidic than the first ones, which means it does it freaking again. And we'd now get a carbon, and I don't feel like, well, I guess I can color code them, with 3 different chlorines connected to it. But now, do I have any more acidic hydrogens?
No.
No. Okay. No one brought up the aldehyde hydrogen. Okay. The aldehyde hydrogen is not acidic. Okay. And if you have questions about that, feel free to talk to me after class. But that one's not acidic. So do we now have our final answer?
Yeah.
Seems reasonable. Sure. Cool. We box it up and say that's our final answer. Okay. So we go into the lab, we run this reaction hoping to get these 3 chlorines on there, and instead we don't get 3 chlorines on it, and we find out that when we determine our actual product, we end up with a carboxylic acid. Ooh, foreshadowing for the something else that some people may be working on. Okay, what the hell? That's not a carboxylic acid. How could I possibly get a carboxylic acid?
The carbon now acts as a leaving with the chlorines leaving group.
I've got 3 very electronegative elements connected to a carbon. Does that carbon want some electrons? Yeah, so it could start to act as a leaving group and remove all of those electrons. Okay? But that would form a carbocation, right? Is that carbocation stable? No? Why not? You can't say no so confidently and then say I don't know. That does not work.
Because it's got a charge on it.
Cool, I accept that. Okay, it's got a charge on it. Can't possibly be stable. And if it can't possibly be stable, what happens? The negative would come right back, and we'd go backwards, and Andrew would be wrong.
Base still and solution.
Okay, so we got a couple different things that could come into play here. We have base still in solution, but a base would require to react with a hydrogen. Do I have any acidic hydrogens?
From her other
From all the stuff that I don't have anymore? Remember, I converted it all across into that upper right-hand corner. So I don't have any more acidic hydrogens. You said hydroxide acts as a base. Is that the only chemistry available to a negatively charged species?
act as a nucleophile as well.
It could act as a nucleophile. So what could it potentially do? It could nucleophilically, ooh, that was really ugly, maybe do something like this. And interestingly enough, what functional group did I just make? There's the carboxylic acid. Okay. Is this mechanistically valid? Now we got all sorts of issues that would drill into the chemistry of what's happening at each of those stages, and not really. Okay. What's that? So we've got a couple things popping up. At the end of this result, I have an acidic hydrogen, which means my base should come through and remove that hydrogen. To get the carboxylic acid back, what would I do? Add an acid. In almost all of our chemical reactions, we neutralize whatever the reagent was that was added in there. Since I added sodium hydroxide to begin with, once this reaction is done, what am I going to do? Add acid to kill off that sodium hydroxide. When I add that acid, that's getting protonated back. That workup stage of our chemical reaction is rarely, if ever, actually discussed, right, in lectures, right? But it's there. Okay. Other components of this looks kind of like what kind of mechanism that we're running here? And you could answer that two different ways. You could answer that as a mechanism. You could also answer that as elementary mechanistic steps. Okay. That whole section you could probably get away with calling an SN1 because you have the leaving group leave, carbocation, nucleophile attack, final answer. When we did all of our leaving groups leave and all of that with our SN1 reaction, how many times did we do that with an sp2 carbon? Never, because shit doesn't happen that way. Right? The reactivity behind this, yes, we have the potential for a leaving group, okay, but we have a larger reactivity in the pi bond. And so our mechanism changes a little bit. Our hydroxide acts as a nucleophile, comes in, breaks the pi bond. What kind of mechanism would that be? Okay, it's an addition because I broke the pi bond. I like the idea of substitution. The nucleophile is coming in and attacking and breaking a leaving group, but the leaving group is a pi bond. Like that doesn't really count as a leaving group. Okay, so it's an addition, but addition is a reaction, not a mechanism. What's the mechanism? It's a nucleophile addition because what caused the pi bond to break? A negatively charged atom, also known as a nucleophile. This changes our output down at the bottom as far as a mechanism goes. I'm just doing 3 chlorines out there now. There's our OH. Okay. You now effectively have 3 electronegative groups connected to the center carbon. That center carbon is a little bit irritated and says, give me some freaking electrons back. And where's the easiest place to get electrons back from? Which oxygen? The charged oxygen. Why the charged oxygen? Because it's charged. That's our Cario aspect, if you want to use it as Cario. So those electrons come back down. When they come back down, we exceed the octet, so what has to happen? You eject a leaving group. And you might say, well, carbon negative is not as good a leaving group as OH negative. Why would this happen? Okay? It's a carbon negative with 3 electronegative chlorines. That's enough to overcome it. Okay? You mean I can't just use Cario outright? No, you can't. This would be one of those cases where I would recommend memorization because it's not just a straightforward order behind it. That produces our final product, sort of, with that negative carbon. Okay? As Tyler was suggesting, we're in a basic environment. We also have negative carbon. How can we stabilize that negative carbon? Mechanistically, it comes in, picks up the hydrogen. We get the negative oxygen, HC. And oh, good grief, we've now done everything formally correct from beginning to end. Okay. Officially, the answer that would be predicted would be the carboxylic acid, but you didn't add H+. That's part of the workup that was implied within this process. I'm sorry, it sucks that way. Sometimes we show it explicitly, sometimes we don't. So this is a whole lot of crap going on. If we consider just that first step that we ran through, we did acid-base followed by substitution, SN2. Then we did it again, and then we did it again, and then we moved to nucleophile addition. What was this unit all about? Nucleophile addition. This step is critical for this unit. You know what's not critical? This next step, because what happened in that next step?
Acid base.
For that box, that's acid base. Did you transfer any hydrogens?
Yeah. One. Hydrogen on the.
You mean over here? You transferred hydrogens?
That stuff? Oh.
Here
that-
to here.
Is that
I formed a pi bond. Where is it? It's over there. That's an elimination. In the process of forming that pi bond, what was eliminated from the structure? A negatively charged things. Negatively charged things are better known as, we just did a nucleophile elimination. This nucleophile addition is a huge part of this unit. Nucleophile elimination is our next unit. This reaction has unit, whatever it is, 3 from OChem 1 up the yin-yang, followed by one step, effectively, that's unit 2 of this semester. Okay? So the vast majority of this chemical reaction, beginning to end, is stuff you already know. The part that we're missing is this nucleophile elimination that we'll see in much more detail in our next unit. So don't stress about that elimination part. Stress about all the other components that stack with it. Kind of, sort of? Okay. Can I erase a lot? Sorry, let me put that back. You can get your picture.
Why did
You're
you say
covered.
the CC came off first?
It didn't come off first, it came off in a nucleophile elimination step. So what we were trying to do is we guessed at a mechanism and said that doesn't match any of our mechanistic detail. What elementary mechanistic steps would match? And we changed how we interpreted it to actually get it to come together. Why does it come off as a leaving group? You have 3 electronegative elements connected to that carbon. It's those 3 elements inductively withdrawing electrons that allow it to be a stable leaving group. Okay, can I erase everything now? So now I want to call out kind of the next level, because I know people want to go through and memorize, and I get it. But I want to make sure you're careful with how you memorize. If we were to look at this reaction, right, that might be what we summarize. Right? So if I now go to this as a chemical reaction, what would I predict my product to be? And I think I heard somebody mumble it. And for sure I talked with somebody else about this. Oh, we get this. We put the carboxylic acid at the end. Is that what we did? Go back and look at what that overall reaction is showing. Where did you put the carboxylic acid? Next to the carbonyl. Not at the end of the structure, next to the carbonyl. It just also happened to be the end of the structure. But if you've memorized that pattern as end of the structure, you draw this. And that is wrong. Okay, well, I need to make it next to the carbonyl. So, ta-da, fixed. Right? Why is that one also wrong? You got a leg up because you asked a lot of really important questions about certain things in this. You may not realize you did, but you did. Why is this also wrong?
There's a missing carbon.
What do you mean a missing carbon? There's a missing carbon in the top one too.
You're saying that carbon CL3 is good.
If we go back to that top reaction, what we memorized was the core functionality on how we converted, but what we decided to ignore in what we memorized was the thing that you asked lots and lots of questions about, which you just followed up with. The other part of that product is I had that CCl3. That CCl3 meant that at that carbon, next to the carbonyl, I had how many hydrogens? 3, so that I could get 3 chlorines. That carbon next to the carbonyl does not have 3 chlorines, which means I never form that leaving group. I never get 3 chlorines on there, which means I never get that nucleophile attack. And instead, what do I get?
Just 2 chlorines for the hydrogens and that's it.
Just those 2 hydrogens are replaced by the chlorines. What happened with this group out here? Good answer, nothing. Why? Okay, I can accept not acidic. What functional group is it? It's an alkane. I'm not doing a radical reaction, which means nothing's going to change with those, which means I still leave them out there, unchanged. Do you see how memorization can get really dodgy depending on what you're looking at to memorize? Okay? Again, it's not bad. Just realize there's weaknesses behind it. You should be looking at both aspects. An overall reaction, what are the components within that so that I can memorize those pieces, but then also acknowledge what are the stages along the way, because I may encounter systems that don't allow me to go all the way. Kind of makes sense? We did talk about this reaction now a lot, so theoretically you would be responsible for both of these. I would argue this bottom one is unit 2, and this top one is unit 3. The only reason we're talking about it is because we can't do 3 substitutions without also saying we're going to have to do these extra steps. So that's why it shows up in the textbook, and it's showing up kind of premature. So could you see questions about that top one on this exam? Yeah, but you're looking really, really limited. Our primary focus should be that bottom case. Make sense? Questions now? Nothing? I got at least a minute.
I'm waiting.
I won't start something new.